chemistry. Moving on to chapter 10. Chapter 10 is a difficult chapter, in my opinion. It's conceptually difficult to understand and to kind of wrap your mind around. It is about states of matter, which you have some knowledge of already, but it kind of gets pretty technical. I would advise you reading the chapter. It will not hurt at all. So the chapter begins with a discussion of something called the kinetic molecular theory. Okay. And the kinetic molecular theory states the following, that particles of matter are always in motion. We've talked about this. Tiny atoms, molecules, are always vibrating back and forth. Okay? The theory is based on 5 assumptions. Now, these assumptions are sort of perfect world scenarios. Okay? They don't, any of them ever happen perfectly, but they develop this theory and this model so that they can develop something called an ideal gas, which we'll talk about a bit later, so that we can compare real gases to ideal gases. These things never perfectly pan out because, again, this is ideal situations, but this model is useful for predicting the behavior of gases. And you'll find that a lot of this chapter is about gases, even though it's about all the states of matter. It really concentrates on gases because the next chapter is all completely about gases. All right, so the 5 assumptions of kinetic molecular theory. Number 1, gases consist of large numbers of very small particles that are very far apart for their size. Okay, that's something we've talked about before. Gases are very low in density, so that means they are very far apart, and that's assumption number 1. Assumption number 2 is that collisions between those particles in a gas, and so when 2 or more of the particles collide themselves, or when those particles hit the walls of the container that they're in, are perfectly elastic. See, here's where the idealism comes in. We never have perfectly elastic collisions. If you'll remember, elastic collisions from, hopefully, physical science, a tiny bit. Elastic collision is a collision that happens where no energy is lost. A moving, particle, in this case, hits another particle, collides with another particle, without any loss of energy at all. Okay, so that's an assumption of kinetic molecular theory, that these particles have perfectly elastic collisions. And you'll see what that leads to down here in number 4. Okay, assumption number 3 is that, these gas particles are in rapid, random, and continuous constant motion. Okay, because they move, they possess something called kinetic energy. Again, hearkening back to physical science, hopefully you remember what kinetic energy is. It is the energy of motion. If an object or a body is moving, we say that it has kinetic energy. Assumption number 4 is that there are no forces of attraction between gas particles. So what that means is they immediately bounce apart after the collision. This actually bolsters assumption number 2 here. Assumption number 4 kind of leads to these perfect collisions, these perfectly elastic collisions. So that's what assumption number 4 is about, that there are no forces of attraction between gas molecules, and they immediately redirect and move in a different direction after a collision. And of course, that is never true in a real world situation, but again, this is a model we've based some other things on. Okay, and the last assumption number 5, is that the temperature of a gas is dependent upon that kinetic energy we just talked about. When those molecules and atoms are moving, that means they have kinetic energy, and the temperature of the gas is based on that average kinetic energy, the average kinetic energy of all the particles in the sample of the gas. And just a little reminder here, kinetic energy is equal to 1/2 the kinetic energy of any object, gas particles, cars, or people in a sprint or anything. Their kinetic energy is equal to 1/2 their mass multiplied by their velocity squared. So you can see that kinetic energy is dependent on both mass and velocity, but mostly velocity because it's squared there. Okay, we're going to take a little break. I'm going to divide this lecture up into small pieces this time. I'll be right back.